So company K, $5 per month, 50 cents a minute. So cheaper monthly, but more per minute. Company L, $10 a month, more per month, but less per minute. So what are the factors here that would help you decide, did I go with company K, company L? Well, what would be the decision factor? Oh, so what do you mean by how much they use their phone? How many, right? So how many minutes, right? So give me an example. When would I use K or L depending on the minutes?
I guess if you use like 20 minutes a month, versus like 100 minutes a month, you would go with something that's cheaper per minute because you're not doing.
Okay, so if you're saying you don't talk a lot, this is an emergency only phone. Now when you got your phones, did anybody get that speech? This is for emergencies only. Did anybody get that speech?
Yes.
I did.
And I don't use it.
Okay, right? So we're not to, okay, I'm with your mom. I agree with her. So she's probably saying, look, this is an expensive device. It costs money. Maybe she doesn't have a plan where every minute is included. So you use it, you need to call me. That's who you need to call. This is not for you to be chatting with your friends on the right? She gave you that speech? Yes, good for her. I knew I liked your mom. I knew it.
Exactly.
My mom did that to me.
Now, did anybody not get that speech? Please, talk to your friends all the time, as much as you like, because we have unlimited minutes, blah, blah, blah. So, it depends if you're an emergency only. Are you going to be using the phone a lot?
Yes.
I hope not. Well, you have a lot of emergencies. Most of us don't. How many times have you had an emergency? Maybe I shouldn't ask that. Too personal.
I screamed.
How many times a month do you say? It's an emergency situation. I got to get to mom. 0.5 times, half a time a month. He gets the call, so it's not a lot.
Oh,
Now those of us who love to chat, just because you're too lazy, mom. Okay.
Mom, I need a ride.
Is she rethinking the phone now? I bet she is. All right. So, how many minutes we use? If we don't use it a lot, which company do you go with?
Okay.
Right? You pay less per month, even though it's more per minute, because you're not using a lot of minutes. What if you are a chatty Cathy? You know what a chatty Cathy is?
Yes.
Yeah, there used to be a dog called Chatty Cathy. And it was not sure. Chatty Cathy. So that's you. Which phone do you want? Which company? Even though it's more per month. Now, my question would be, when does it make more economic sense? What's a lot of minutes? What's a little minutes? Right? That's what we're trying to find out here. And thank heavens for math. Math to the rescue. So let's see how math can help us. Because math is better. Oh, did I say that out loud? All right, so write equations that describe each phone plan. All right, let's think about this. How do I figure out the cost? If it's $5 per month and 50 cents a minute, so per month, what's the cost? Depends on what? How many minutes? So let the minutes be our X. So here's our first plan. To figure out my phone bill, what are they going to do for company K? The cost, and let's call cost, I don't know why. What is my repeating cost? Is it the $5 per month or the 50 cents?
The 50 cents.
So it's 50 cents for every minute, but what else do I pay every month? So was this the cost of company? 50 cents per minute plus the $5 I have to pay.
Yeah.
So what is my cost then for company L?
It's 5x plus 10. Yeah.
25 cents for every minute plus that $10 fee. Does this make sense?
No. Yeah.
It is, but does it make sense where I got it? Right? The minute times how much it costs per minute plus that monthly fee. That's what you pay every month, right? So let's see, let's graph them and see what happens here. So I think I'm going to try a different columns here. So let's see, I'm going to rewrite that as y equals half x plus 5. Right? Because it's easier to graph when you have the fraction, right? So m equals half and b equals 5. So let's see how that works. Okay. But look at my scale here. How about this? I'm going to change this to be 10 over 20. Is that the same as a half?
Yeah.
Will that make it easier on my scale here?
Yes.
So 10. Well, that's 5 10. 10 there. So this is company K, right? Oh, I'm trying to make this one.
That's a lot of money.
Yeah, this is what the cost, the more you talk, the more it costs. Alright, and let's try, hang on a second there, Jerry, hang on a second. So L, what? Did I do it wrong?
No.
Did I make a mistake? No. No, because this scale is like 5 each and this is 10 each, a little confusing the scale on this one. A little hard to see, but my M is 1/4 and my D is 10. So I'm going to start at 10, right? This is company L. And let's see, let's make it 10 over 40 because it might be a little easier to see. So I go up 10, 10, 20, 30, 40. So let's see.
Let's go company L.
Okay, so here's company L. Where do I break even? And what do I mean by that? Where does it not matter if you go with company K or company L? Where is that on the list? At 20 minutes. Now that's this, right? Yeah. The point where they intersect. So what is this? This is 20 minutes, $15, right? So if you go, I know exactly how many minutes I'm going to use. I have 20 emergencies every month, 20 minutes, or I know I have 20 friends and I talk to them for 1 minute each. 20 minutes. Which plan should you go for? Well, I'm just saying, like, you have to make a decision here. Which plan should I get? So you know what? I'm never going to talk more or less than 20 minutes. I'm always going to be about exactly that remark. It doesn't matter, right? Now, you're right. How often is that the case where you know I'm going to talk exactly 20 minutes a month all the time? You don't. So let's say you're the emergency person. I only use it in an emergency. Which plan might be better for you if you like saving money? This guy, right? Because look, it's less than the other plan when you're less than 20 minutes. Now, what about if you are a chatty Cathy? I talk all the time. You cannot shut me up. Which one do we want? Because in the long run, it's going to be cheaper. So this is an example of what we call a linear system. See how I had two equations here? The x and the y mean the same thing. The x are the number of minutes that you speak. The y is the cost per month. They mean the exact same thing. And I'm kind of looking for where are they the same, which is what we call a solution to a linear system. And how can this information help me make decisions? So I want us to kind of remember this example because we're going to be spending a lot of time finding that point where they meet. But this is really used a lot in real life, the idea of linear systems. GPS, anybody have GPS in their car, on their phones, right? You got the fancy phone with GPS on it? So, it's like, okay, turn left and that thing? GPS is actually a linear system. I think it's a three-dimensional one, an X, Y, and a Z. Based on satellites in the sky, right? They know, well, but they're in the sky. It's a three-dimensional thing. There's many satellites in the sky. And they figure out where you are on the ground based on a linear system. So we use them in real life in that and in other things and making decisions like this. So we're going to learn how to solve them. So what is a linear system? A linear system, it consists of two or more linear equations in the same variables. So what do I mean by that? These are variables x and y, so is that one. Linear system of two equations here. A solution to a linear system is an xy pair, and it satisfies each equation in the system. Now, what do I mean by that? So this is an xy pair, 20, 15. And what do you think I mean by it satisfies both equations? What do you think that means? Satisfies it. Makes it happy? Maybe? What it really means is it's a solution. So how do I know if something is a solution to an equation? Yes? Yes? I saw something over there. What? Plug in. Plug in, that's the one I'm looking for. Plug in. So I have y equals half x plus 5, right? That's my first one. How do I know if 20, 15 is a solution? Well, the y is 15, and the x is 10, right? Let's see if it works. I'm just plugging in the x. The x goes here, and the y goes here, right? X right there. Oh, plugging it in to this first equation. Let's 15. What's half of 20? 10 plus 5? 15. So it works in this one, but it has to work in both. So then it's not a solution. This should be a 15. I'm plugging in the 15 where I see a y, and a 20 when I see the x. So is 15 the same as, well, let's see, what's 1/4 of 20? 5 plus 10. So what this means is 2015 is a solution to both. And isn't it? You can tell by the graph. You can tell by the graph. So solutions are where the graphs intersect. And here's an example. So I've got a linear system here, two equations, 2x plus 3y equals 6, negative 2x plus 4y equals 8. Is 2, 3 a solution? How can I tell? Plug it in. 3 times 3. So this is the first equation. Wherever I see an x, I put a 2. Wherever I see a y, I put a 3. And what is that? We're getting 13 equals 6. Nope. Does not. So is this one a solution? No. I don't actually need to test the second one. Let's say it worked in this one. Then you would have to check to make sure they both do. What happens if it does work in this one? Doesn't matter if it doesn't work in this one. Let's try 0, 2. So you plug it, the 0 in for x, and the 2 in for y, right, to this one. You're getting 0 plus 6 equals 6. Hey, that worked. So is this a solution to the linear system? I don't know yet. Why don't I know yet? Because I have to check the other one. So negative 2x plus 4y, does that equal 8? Well, that's a 0. Yes. Right, they match. So now I can say, yes, 0, 2 is a solution. Now what do I mean by that? I mean if you were to graph both of these, and I don't know yet what they look like, but you know where they're going to meet? Over here at 0, 2. It's where the two lines intersect. That's what I just found. Solutions to linear equations occur when lines intersect. So here's the line 2x plus 3 equals 6. I graphed it. Here's the line negative 2x plus 4y equals 8. And here at 0, 2 is the solution to the linear system. It's the xy pair that works in both. And does that make sense? The 0, 2 is a part of this line. 0, 2 is a part of that line. So it's the point on the graph where they intersect. And one way to find the solutions, and we're going to learn 3 different methods for finding solutions to a linear system. One way that you can really see is graphing the line. So who's good at graphing lines? Not that many. Uh-oh. Yeah, okay. Oh, yeah, we're good at it. If you're good at it, this will be easy-ish. So method 1. No. Graphing. Here's what you do. Graph both equations in the same coordinate plane. Estimate the point of intersection. Estimate. Estimate. What? I'm basically saying look at the graph and find the point. But depending on how you graph or where the point is, this might be a little difficult. Check your estimate by substituting into both. And I can't emphasize. Let's write this down. There, everybody writing this down? Verify solutions. You write this? Because I don't think everybody write this. Verify solutions by plugging, xy values into both. And do whatever you need to do to emphasize the word both, the original equation. If you need to circle this, or if you have another color, if you have a highlighter, both is important. Checking one of them is not enough. I guess unless it doesn't work. But to prove that it does work, they have to work in both. Now, we writing this down? You're getting in there as important. Stars, exclamation point, whatever you need to. It's important. You got that? We're still going. Alright, so let's do the example on your paper here. So everybody's going to do this with me. So I've got 2 equations. I want to find the point of intersection. Andrew, would you mind showing me the So step 1, graph the equation. So this is where being good at graphing comes into play. How do I graph this? table of values, intercepts, or y equals mx plus b? What do you want to do? Y equals mx plus b? Good answer. How do I do that? Because it's not in y equals mx plus b form. Yes, I do. How do I do that? Yeah, let's subtract 3x. I'm getting negative y equals negative 3x plus 2. My God, is this in y equals mx plus b form?
No.
What's the problem? Is that how I fix that? By what? Negative 1. And what's going to happen? All your signs will change. Multiplying or dividing everything by negative 1, everything changes sign. If it's negative, it went positive. If it's positive, it went negative. Are my y equals mx plus b form? What's m? And what's b? So what do I do? I go to negative 2. That's my y-intercept. Okay, so we all doing it? And then, so that's really 3 over 1, up 3, right 1, or down 3, left 1. So 1, 2, 3, up 1. I'm actually going to stand back here. I have a hard time standing up from there, so I'm going to try it from here. Okay, so 1, 2, 3, 1, or I can go down 3. So if I miss one. Okay. Wow, that's a mess. Okay, pretend that met up. That's my slate. I'm not very good at it. I'm trying to connect the dots, so you can connect your dots a little bit better. Whoa! Yeah, that did not work out so well. Now here's my second line. Is this in y equals mx plus b form? No. So I'm going to subtract x from both sides, yes? Subtract x, subtract x. What's my slope? And what's my y-intercept? 2, 3, 4, 5, 6. Okay, then what? Now this is a down 1, right 1, or an up 1, left 1. Up 1, left 1. Up 1, left. So now if I had drawn these correctly, see if I can get this line a little bit better. Oh, I cannot. But where's my point of intersection? Probably your picture's a little bit better. So that should be the solution to this linear system. It's a point on both the lines, right? How do I know it's right? Verify the solution in both equations. So we're going to substitute in. Now go back to the original. And what I mean by original, these guys right here. Why original? Why can't I use these? What's wrong with this one? And what's wrong with that? Why can't I? Well, I could. The answer to that question is you could. Why might I maybe not want to? And you're on the right track here, Andrew. Why might I not want to use these two? Oh. I did, but aren't they equivalent? Yeah. I could have done it wrong. Exactly. Now, if I did this right, sure, go ahead, use it. But did anybody ever make a mistake ever? Putting something in y equal form? Oh, really? Just you and me, Quinn? We're the only ones ever. Oh, I see. Thank you. Every hand should be up, okay? Let me tell you. Sometimes you make a mistake when you put something in y equal form. So this will help us find it. Maybe we did. So let's see. We'll go back to the original. 3, I think x is negative 1 minus y. Well, I think y is negative 5. Is that the same as 2? Negative 3. What's a negative negative? What's up with 5? What's negative 3 plus 5? Hooray! So I'm done checking, right? Wrong! Right? Check the second equation. So that says that x plus y, we need it to be negative 6. Well, what's negative 1 plus negative 5? Yay! That's negative 6. Now I know I have the right solution. So it's a little bit of work. It's not so bad. Is it? If you know how to graph, is it bad? You don't know how to graph exposure. Okay, so we verified by putting into both equations. We already did that. This one is not on your paper, but just let's see if we can do this. Just as another example, I want to graph both lines. So let's see, if I want this in y equals mx plus b form, put everything over except for the y. Y equals x minus 7, so what's m? What's b? So I go down to negative 7. 1, 2, 3, 4, 6, 7. Slope is 1. That's up 1, right 1, right? Up 1, right 1. So we can kind of draw those sides. Or down 1, left 1. And again, I'm having a little trouble with my, someday they'll fix my board. I don't know when that day will be. Let's look at the second line. Again, I'm solving it for y. Subtract the x. 4y equals negative x minus 8. How do I get y by itself?
Y before.
And what gets divided by 4? Everything. Might have to put the little invisible 1 here. So I can see I have y equals negative 1/4 x, which minus 2. Why minus 2? Negative 8 over 4, right? Negative divided by a positive. So what's my m? Negative 1/4. And what's my b? So I go to negative 2, my b. Down 1, right 4. Down 1, right 4. And we 1, 2, 3, 4. Now I can see my point of intersection, can't I? So what is that? 1, 2, 3, 4. Negative 3? How do I know it's right? Go back to the original ones. Oh, what else? So negative 4 plus negative 3, is that the same as negative 7? Negative 7 is a yes. Great. Try the other one. Do not forget to check both. 4 plus 4 times negative 3. I sure hope that's negative 8. So let's see. That's a 4. 4 times negative 3, that's a negative 12. Is that the same as negative 8? Yes. Yes, it is. So I know I have the right solution. So solutions to linear systems are where the graphs intersect in x, y, and or the solutions are x, y, and z. What do you think? Question? Sure. Yeah, okay, you're on the U-tries already. I'm just going to tell you to skip that one because the graph's a little hard for that one. So yeah, she's looking at, she's ahead. She's looking at the U-tries. I'm going to go with the skip for now, only because the scale is making this a little bit harder. I actually want you to start with C. So start with this guy, and I want you to try this, and then go on to letter B. Let's try this one. So x minus y equals 5. So, well, I guess I'll subtract this. Negative y equals negative x plus 5. I don't want that. I want y equals. So multiply through by that negative 1. Every sign will change. Y equals x minus 5. That what we got as equivalent is x minus y equals 5. So what's m? Right there? And b is negative 5. So I go down to negative 5. And then 1 is up 1, right 1. Up 1, right 1. Up 1, right 1. This what we got? No? Well, who's right, me or you? Well, I don't know about that, but I think this one I am. See if you can find your mistake. Now for this guy, I subtracted 3x, right? And then I'm there. So m is negative 3, and b is 3. So 1, 2, 3. Negative 3 over 1 says go down 3, right 1. 1, 2, 3, right 1. 1, 2, 3, right 1. And I'm seeing where it's sitting. It is over here. It's hard to see on my graph, but it is 2, negative 3. Check it. 2 minus negative 3. That's 2 plus 3. That's 5. 3 times 2 is 6. Minus 3 is 3. It's magic. You have to check them. Have to. Okay. We can do B. How do we do with B? Did we get it? Oh, let's see. I have to add x, right? So what is the hard one? 2x equals, 2y equals what? X plus 3? So y equals half x plus 3. No, that's really. What you got? Yes.
So when you check it for the 2 points, does the answer like y equals 1, does it have to know 2 numbers?
This is how you check it. See x minus y equals 5? So you plug in the 2, you plug in the -3, and you have to have a true statement when you know that. So what's a minus minus? That's a plus. So does it work?
Yeah.
And then you have to do the same thing with the other equation. Oh, well, this is an ugly one. So let's see, that's 3/2, that's 1.5, right? And then I have to go up 1, right 2. Up 1, right 2, or down 1, left 2. Down 1, left 2. Oh, I'm trying to make that fit. Alright, now y equals -2x plus 4. I just subtracted 2x from one side. 1, 2, 3, 4. Down 2, right 1, down 2, right 1. It does, but you know what, it's a little hard to read. And why is that? Because I'm not right on an integer value, right? So when that happens, that kind of messes stuff up. So we make a guess. So when I say estimate the point of intersection, you do your best sometimes. Sometimes it's really hard to tell. And it looks like 1, too. It looks like it. So isn't it really, really important to check it? Yeah. Because I could be wrong. So you check it. You say, well, -1 plus 2 times 2. I sure hope that's 3. Well, it is. -1 plus 4. So it worked in the first one. Now I need it to work in the second one. And again, I'm just plugging in the x's and the y's into the original equations, and it did work. So what is a downside to using the graphing method? Whoops. Okay, we'll get it. But what's a downside to it? Yes, sometimes it's not as accurate. So when you don't have nice integer values, what if we were to graph this, and not this one, this one actually works, but let's say I was graphing one, and my intersection is kind of in the middle-ish. Can you actually read what that point is? I don't know. It could be 0.5, it could be 0.2, it could be 0.1117964, right? I can't read it. So the downside to graphing is that it's not always in a nice little package. You know, 2 comma -3 isn't that nice. It doesn't always work that way. But what's good about it? What's good about the graphing method? Yeah. Yeah, it's very visual. I really like it because it reminds us that the solution to a linear system is an ordered pair where they intersect. Now I want to show you something here. Remember this guy? We played with this a little bit last time? Yeah. Now you can use your calculator to help you. I'm going to use the calculator to help me here. Now the problem with the calculator is, remember, these are all y equal form. So it doesn't help me with the original equation. But like, let's say this one where I know what I think I know what they are. So y equals x minus 5 was one of them, right? Y equals x minus 5. And then what was the other one? -3x plus 3. So if I type in the equations in y equal form, right, I'm doing C here with this. What happens when I graph? Well, now first of all, doesn't that give me a good feeling about what I did graph? And they kind of match, that's great. Now wouldn't it be nice if this could just tell me what the point of intersection was? That would be so nice. Wait a minute. So remember how we were doing zeros before. How did we get there? Now remember that little calc thing? Press the second button, and if you look at the trace, here it says calc. Which one do you think I want to find the intersection? Intersect. So you press number 5. Now it's going to ask you a couple of questions. First, curve. Now lines, I guess, are curves. So things that you graph are called curves. So see where it's blinking on this line? Is that my first curve? Sure. Hit enter. Second curve. See where it's blinking? Is that my second line? Hit enter. Don't guess. 2 comma -3. Is that what I got? Yes! You mean I can just use this? No. I mean, you better show me that you know how to do this. But what's to stop you from saying, wow, did I do this right? Type it in.
Oh, do you want to verify?
Yes, you do. Things I'm looking for all these steps. You graph the equations correctly, you found the right point of intersection, and you verify. You betcha I'm looking for verification. But this is your final verification, which is, I just want to make sure that I didn't mess up every single thing here. Sometimes it helps you, like you ever do it where it seems to be right and then your verification doesn't work? Stupid job. So it's another tool in the tool bucket. So it's really good to know how to do that. All right, so looking at graphs, sometimes we have a point of intersection. How many solutions to this linear system are there? I am on the back here. How many solutions? If a solution is the point where the lines meet, how many solutions are there? One. This one. Okay? So sometimes we're going to have one solution with a linear system. I'm going to get rid of this guy. Now let's suppose that I have, and they may not come out looking like it, but let's say I have parallel lines. How many solutions? None. How come? Why are there no solutions to parallel lines, Claire?
The parallel lines are like straight across and they're not.
And remember, solutions are where lines intersect. So where do these lines intersect? They don't. So sometimes there are no solutions to linear system. Now let's say here's one line, and I'm going to draw another line. This line is meant to be on top of the other line. How many solutions do I have now? Where do they intersect?
Everywhere.
Everywhere. So it could be, when you're solving these, that there's one solution, there are no solutions because the lines that you're looking at are parallel, or an infinite number because it's one line directly on top of the other. And this sounds a little bit familiar. Remember we were solving equations with variables on both sides? Yes?
No.
Yes. And remember when we had something like this, 2x plus 2 equals 3x minus 5, and we said there were no solutions? Algebraically, the x's would drop out and get some kind of nonsense. But remember when we started this, you can graph these. Now what do I know about these lines? They have the same slope and different y-intercepts. They're going to be parallel. No solution. So it all ties in. It all ties in eventually. So I'm going to skip this next little bit here. I don't have to worry about that. But linear systems are two or more linear equations in the same variable. Solutions to linear systems are the coordinates of the intersection, if there is an intersection, of the lines in the system. And the way we solve by graphing is you graph both equations on the same coordinate plane. You estimate that point of intersection. Sometimes you're going to know exactly where it is. Sometimes it is a guess. When it's not, exactly on the little intersection of lines there. And then you verify that point by plugging it back into both original equations. That's how you check. Now this step here, to verify, well, okay, I'm trying to circle that. I'm going to be teaching you 3 different methods. You always end with this. You verify that point by plugging it back into both equations. I have a little trouble. With this guy here. We have a couple minutes. We can start the next little part here. So this is the graphing method. So just again, good. I think Tori pointed this out. What's good about the graphing method? It's very visual. You can see it or not see it, right? It's parallel. What's maybe not so good? Well, there's a lot of steps. I'm not going to say no. Hard if you don't have a graph. Sometimes you can't tell the solution. You can't necessarily tell what the exact solution is all the time. So what do I mean by that? That's when you have 2 lines, they meet, and let's say it's between -1 and -2, and it's between 3 and 4. I don't know, is it -1.5? I don't know. So it's a guesswork sometimes. So we have to have other ways to do it. And we're going to learn 2 algebraic methods. 2 algebraic methods. Yay, algebra! We're going to do one of them today and work on the next one. The first one is called the substitution method. What do we think the substitution method involves? What do you think it involves? Substitution. Exactly. And I guess I'll have to keep you in suspense. Now I get you to come back after lunch. I have this. So we're solving using substitution. First step, solve it for y or solve it for x. Now look what I've got here. This one is already solved for y. So I don't really have to do step 1 in this case. If this had been written negative 3x plus y equals 2, and x plus 2y equals 11, you would have another step, which is to solve for either x or y. Now, how do you know which one to solve for? It doesn't matter. I always look for what's easier. So if I see a y or an x that has just a coefficient of 1, that's the easy one to solve for. I would add 3x to both sides, and I get y equals 3x plus 2. Now this one already came that way, I don't have to. That's good. Now what do I do once I have that? Is I'm going to substitute the expression. So equals, really think about what equals means. It means same, right? Same. So the y value, wherever you see it in the system, is the same as 3x plus 2. These things are the same. Believe that? Convinced? They're the same. That's what equal means. So now let's look at this guy. Y is the same as 3x plus 2. X plus 2y equals 11. So y is the same as what? 3x plus 2. So what I'm going to do is, instead of writing x plus 2y equals 11, right, that's my second one, I'm going to write what y is the same as. It's the same as 3x plus 2. That's the substitution. Did we all watch that real closely? No. But this is the confusing part, if there is a confusing part, which is find what y or x is the same as, and then substitute that value into the other equation. Because when I do that, look, I now have an equation in one variable. You know how to solve an equation in one variable? Say yes. Yes. Of course we know how to solve an equation in one variable. We've been spending a lot of time doing that. How do I solve this? Yeah, I'm going to distribute, so I'll put it over here. X plus 2 times 3x. 2 times 2 equals 4. What's my next step? Combine like terms. I've got an x, and I got 6 more x's. How many x's? And then 7x to subtract 4 from both sides, right? So what's x? Now what do I just find here? This is 1. Remember what this is. Now even though I'm not graphing them, what is the solution? It's the xy pair where these two lines meet. So it's an xy pair. That's going to be the solution. What's the x value? 1. You just found excuse me, you just found the x value of this xy pair. Now how do I find the y value? I plug it in where? See this guy? Now you can plug it into either one, doesn't matter which one. But I know what x is, right? Can I find y now? Right? Y equals 3x plus 2. I believe x is 1. So let me plug it in. What's y going to be? 3 plus 2. So that is step 3. Substitute the value that you found in step 1. In this case, we found x to be 1. Back into one of those equations. And then solve that for the other variable. And then once you've done that, I've got a solution. If you were to graph these, they would hit at 1, 5. How do I know it's correct? Plug it in. So the verification step is the same as it was for the graphing method. So let's see, if y equals 3x plus 2, and y is 5, and x is 1, at least that's what I think it is, and this should be a true statement. So the left is 5.
Could you spend each out in the house office, please?
Okay.
Thank you.
Okay, so that one works. And then what's my other equation? X plus 2y equals 11. So x is 1, 2 times 5. I sure hope that's going to be 11. It is. So I checked them. Checked them. Yes.
Can you do how you find y?
Yes. So did we see how we got x? Yeah. So now I have two equations. Y equals 3x plus 2, x plus 2y equals 11. So I think I know what x is. I think x is 1. Pick one of the equations. Let's pick the other one. X plus 2y equals 11. I think x is 1. Let's solve that for y. Subtract 1 from both sides. Solve it for y. So you plug it into the equation and then find the other variable.
So this is how you do it in the first one, is it?
Yep. Let's try the other one. Y equals 3x plus 2. So y equals 3 times 1 plus 2. 3 times 1 is 3 do it in either one, and we're gonna check both of them anyway. Even the one that you kind of did it for, well, I checked that one sort of, I still check them both. Plug in X, Y, in, make sure it works. I think I have another example. I'm trying to see if I do it. That's the same one, right? Let me do one of the U tries, just to kind of do another example on the U tries on the bottom of the page. So I've got X equals 2y minus 6, 4x plus 6y equals 4. So step one said make sure one of the equations is either x equal or y equal. So do I have that? Yes, right? X equals. Great. So x is the same as what? This. Now notice how I'm putting in parentheses? Because that is a 4 times this whole thing. So it is going to be a distribution. So wherever I see an x, I'm going to put in its equivalent value, 2y plus 6, into the second equation. Who has a question at this point? Because I think this part can be a little confusing. Yeah? Question? This is the same as x, right? This is 4x plus 6y equals 4. I'm just rewriting this one. Except what is x the same as? 2y minus 6. I'm substituting those values. Once I have that, I have an equation in one variable. That's why we're spending so much time on equations, because you have to be good at them to do all this stuff. So I'm getting 8y minus 24 plus 6y equals 4. All right, 8y plus 6y, right? I'm combining my like terms. You have 8 y's, and I give you 6 more y's. How many y's do you have? 14 y's minus 24 equals 4. Then what? Add 24 to both sides. 14y equals 28. Divide by 14, divide by 14. Y equals 2. Now, what did I just find? Right? Remember, the solution is an xy pair. If you were to graph them, the solution is where they meet. The y value of that point is 2. That's what I just found. Y equals 2. Now, how do I find the x? How do I find the x? It's one of the equations. Which equation would you like to do? Yeah, this one's a little bit simpler, but it doesn't matter which one. So x equals 2 times 2 minus 6. So x equals 4 minus 6. What's 4 minus 6? Negative 2. So what's the solution to this linear system? Where do these two lines intersect? At negative 2 comma 2. Now how do I know I'm right and I didn't make a mistake somewhere? Yeah. What's the word? 3 words! Plug her in. Plug her in. Because, alright, so let's see if it works. X equals 2 times 2 minus 6. Let's see. What's x? What's x? That's a negative 2, sorry. So let's see if it works. What have I done? I don't know. Alright, is negative 2 the same as 4 minus 6? Yes. Now, you can say, well, you just did this one. I know. I do them both again, just to be sure. And then I say 4 times x, well, I think x is negative 2, plus 6 times y, that should be 4. That's negative 8, and that's 12. Is that the same as 12? Yes. Do I have to check both? Yes. Yes. I'm doing the first one you tries on the bottom of the page. Makes sense. Now, so this one, I'm just looking at this one real quick, just see, but you are going to be trying this in a moment. But what do I have to do with C that we haven't had to do so far yet? One of the equations doesn't necessarily have to be in function form. You can make it x equals. And as a matter of fact, I think that might be easier. Because how do I get this into x equal form? You know, add y to both sides. You can do it this way, or you can make it a y equal, or you can change this one. Let's say you want to change this one and make it negative 2y minus 6. Then that x would go up in here. So you change one of them and make the substitution in the other equation. Anyway, give them a try. Give them a try. Let's try them and we'll talk after. So try these guys. Okay, so we're going to please do some of these both times. So these are a little hard to see. I've got the little answers up here. And then it's $2 a lesson. Let X be the number of lessons, right? If you're not a member, the lessons are $6 each. So I can write a system of equations. Here they are, right? $2 a lesson plus the $40 you pay to join, $6 a lesson, right? Now, what are you trying to do? What is the total cost of lessons where it's the same? When doesn't it matter? Now, you can graph this and look for the point of intersection, or you can use substitution. Now, watch this for substitution. Notice how they're both y equal? They're both in y equal form, right? So that means wherever I see a y, I can replace it with this. So what's going on this side? And then what's on this side? You can set them, this is the transitive property of equality. If this equals this, and this equals that, then this equals that. Okay, subtract 2x from both sides. 40 equals 4x. Divide by 4. X equals 10. Remember, 10, that's the number of lessons. So if you know you're having exactly 10 lessons, should you join?
No.
Maybe. It makes no difference, right? Now, what if you're going to take more than 10 lessons? Then you should join. But if you're taking less, then you should. Right? That's the kind of information this gives you. Yeah? Maybe? Yeah. All right. Okay, I need to kind of give you your homework. Try this one. Try this while I'm